Hey guys, how's it going today? Figured I would make a video on small signal analysis. Watched lots of videos on it. It's been a long time learning how to do it, but the problem that I was facing is that the videos that described it, they didn't actually break a real circuit down, and I had a hard time. Took a lot of practice and a lot of trial and error to figure out how to do it reliably and accurately. So I figured in this video I would make a video here and I would make a real circuit and simulate it, performing a small signal analysis on it step by step. And hopefully, if you guys are struggling with this in your coursework, it'll help you get through it. So yeah, if you guys would like, share, and subscribe, I'm gonna try to start making more videos. I've been pretty intermittent about it, but I'm gonna try to be doing this more constantly and putting more effort into it. Uh, my problem is I can never finish anything. I have a radio from like 1938 that I restored, and it still doesn't have a knob. I've done everything else. I painted the chassis, changed all the caps, got it working, modified it so I can use it as like an amplifier, and still haven't got a knob for it. That's just me. You know, I've always had a hard time finishing stuff. But if you would, please like, share, subscribe, show some love. Appreciate it. So the first thing we need to do is we need to open a new schematic in LTSpice. And this is where we are going to create our amplifier. So first thing we need is imagine that this voltage source that I just placed is an antenna that's providing a signal. And then we will represent the source impedance of this antenna with a resistor here. And so we're representing that. We're going to call this 50 ohms because that's a very common value for antennas. And then what we're going to do is we're going to place a capacitor in series with it as well. And the goal of this capacitor being here is to block any DC from being able to get into the antenna. Not good things would happen if that happens. So we're not going to do it. So we have a capacitor here. Now I'm going to explain this later on, but for now I'm just going to put these capacitors right here and tap them to ground. We're going to put an inductor here, and I will explain what this part will do later on. All right, so that's pretty much it for the input side. So you could think of this as like the front end of a radio receiver. Now let's work on our amplifier. Plop down an NPN transistor right here. We need to set up the DC side of the circuit. So we'll put a resistor here and another resistor here. So these are going to be our base resistors, and what they're going to do is they are going to provide a voltage divider for the base. And they also, when you have two in series, when you have two, one between the voltage source and one between ground, it helps stabilize something called beta. And I'll explain that in a little bit further detail too when we start doing our calculations. So now we got, this is called your collector. So this is an NPN transistor. So this is the collector. This is the emitter. And then this is the base. So what happens with a transistor is you flow a small current into the base and it induces a larger current from the collector to the emitter. So a little current from here to here will create a big current from here to here. All right, that's the long and skinny of amplifiers. But we'll put a DC voltage source here. We'll call that 12 volts. Collector resistor, probably want to make it something like 1K. Then we'll do 100 on our emitter. I need to put a ground down here. Wire this up to here and here. Boom. Let's see, I'll just connect these terminals together. Beautimous. Now I'm going to leave the signal disconnected for now Let's go in here and let's do sine. We'll make it 1 megahertz, so 1 million hertz, at an amplitude of 4 millivolts. We'll say that's a pretty big radio signal, but this will be okay for now. We'll also install a capacitor here. What this will do is this will increase the AC gain without affecting the bias point. So this provides a low impedance path for the alternating current portion of the voltage that's on this transistor. It gives it an easy path to ground, and that helps increase the gain pretty substantially. We'll just make that 0.47 microfarad. I don't know what a good value would be, but we'll just kind of play with it and see. C5, this is going to be the output capacitor. And then we will put a load resistor here. And so this is going to be the load. This resistor here is going to represent the load that we're driving. We can make this 1.2K, something like that. These, I'm not going to know values for this until later on. But we can make this one a 0.33 U. And let's make this one a 0.33. Actually, let's change this to 0.47. That's where our signal is tiny, so we don't want any attenuation there at all if we can help it. All right, so now that's our circuit. So what we need to do is we can go to Desmos now. I think we're pretty much done here. First thing we're going to do here is we're going to label some of our constants. We're going to create variables here. So RC is 1000, R sub E is equal to 100, RB1 is equal to 50K, RB2 is going to be equal to 10K. I'll just call the coupling capacitor CC, and that's equal to 0.47 times 10 to the power negative 6. Then we have C bypass, and that is equal to the same thing. We'll call the 50 ohm resistor here Z source. C load, that's our load capacitor, 0.33. And then we need RL, that's equal to 1200. Looks like we've done all that right so far. Okay, cool. I don't think we really need our voltages yet. So let's get started here. So we have this signal coming in. What we need to know now is we need to know our DC base current. So let's go ahead and simulate here. Make our stop time like 0.1 or something. Let's tile this horizontally. All right, what is our base current? So our quiescent base current is 63.89895 times 10 to the power of negative 6. So that's microamps. Then we need to determine our DC collector current here. So let's go up here and measure that. 6.389. Yeah, so the beta is just 100 here. So these are all of our components. So what I can do now is I'm going to put a separator here. Then we're going to do beta and GM. Now, normally beta is expressed with the Greek letter for B, but I don't have the option to do that here. So we're just going to go with it. But beta is always equal. It's the ratio between the DC collector current, IC over IB is equal to beta. So, but yeah, beta is 100 exactly. Now we have another one. GM is something called transconductance. And so what transconductance tells you is basically it's referred to as dynamic voltage gain. So it tells you if you change the base voltage by a given amount, you should expect a change in collector current that is proportional to that. And this GM is what relates the base and collector voltage to one another. All right, so GM is always expressed as DC collector current divided by something called VT. And VT is something called thermal voltage. It's usually around 26 millivolts at room temperature. So it gives us a GM of 245, which is in the units. They call it millisiemens, if you're curious. But basically, you can think of transconductance. If you have a transistor, it has an exponential IV characteristic. So it's like, no current, no current, no current, and then it turns on rapidly. All right, so GM will tell you the slope of that line at the DC operating point. So, and that, it's dependent on your collector current. All right, so we got VT there, we got GM. Now there's another important parameter called R pi, and that's essentially the dynamic small signal impedance that the transistor, the base emitter junction, will offer to the signal. So it's essentially how much resistance you would see looking into the base of the transistor to the emitter. And R pi is always determined by beta over GM. All right, so that's 406 ohms of resistance between the base and the emitter. Now, you shouldn't take that literally. This is only valid in some cases. If the input signal gets too large, this will no longer apply. You have to make sure that the transistor is in active mode, which means it's somewhere between being on and being off, and you also have to know that your signal is not too large for it. So R pi. What else do we need to figure out? That's pretty much it for now. So that is our DC. That is everything we can do with a DC pure analysis here. Let's keep going. Next thing we need to do is we need to find values for this. This little tank circuit that I've built here, uh, what its role is it's a pi network is what they call it. And the reason they call it that is because this shape kind of looks like the Greek letter for pi. So the name kind of stuck, I guess, back in the day. So let's go ahead and connect that in here. And what we need to do now is we need to find a few values. The first of which is the reason that let me start here. The reason this pi network exists is because you have an antenna that has a source impedance of 50 ohms, and then you have whatever impedance this portion of the circuit, the input of this amplifier, looking from here to here, what type of impedance you see looking into the input of this transistor. And those do not match, most likely. So usually the base of a transistor is a pretty high impedance input. So anyway, we've got something that we're going to come up with here called Q of the source. And what that will be is we will have to choose. Actually, let me start here. We will choose like kind of an arbitrary value here, and we'll call it Z center. And this video is not really about pi networks, so I don't want to get too deep into all this, but we'll just make it 10 for now. Q, if you would like me to delve more into that, definitely can. So anyway, this Q center, or no, Q of the source, going to be equal to the square root of the input impedance, Z sub S over Z center. Then we need to take these two numbers and subtract 1 from them. So that gives us a Q for our source of 2. Now we also need a Q for our load, and we will not have all of the necessary stuff to calculate this yet. So I'm going to make this 0 temporarily. I'm going to come back. So what we need to find now, in order to find our Q of the load, what we need to do is figure out the impedance from here to ground. All right, so let's say we'll just call this Z input. And what it'll be equal to is, if you remember, I'm sure you probably heard this before, but with an AC signal, a DC power supply basically looks like a dead short to it. Reason being is that if this is a power supply, there's going to be a large filter capacitor present between the positive and ground. And the AC signal, that looks like a dead short to it. So we need to short this out when we're thinking about AC and just pretend that it doesn't exist, just to pretend that there's a ground right here. The other thing is, most of these capacitors we can neglect here because this is a 0.47 microfarad. At 1 megahertz, that's going to be a really low impedance. So it's almost as if we can discount it. So for this one, and even this one, it's almost like they don't exist either. But these down here, they're going to be a lot smaller, so they will present a decent enough impedance that we need to consider it. So Z input is going to be the parallel combination of RB1, and we can do that by taking the inverse this way. Then we can do RB2, same deal. And then we need to add in this. So we have another branch here because current can flow through the base into the emitter. We need to account for it as well. So we need to add one more term here, and that is going to be R pi. And then really we could just make it R pi. That should get us close enough just because this capacitor basically renders the emitter as ground with AC. So let's just neglect that for now. We'll do this to the power of -1. So our Z input looks like it's going to be about 387, 388 ohms. All right. So now that is our load impedance, technically. For this antenna, that is going to be the load impedance of it. So now for this QL, it's going to be square root of the load impedance over Z center. So let's do it like this. And same thing here, we need to subtract 1. Okay, so it's 6.1479. Now, the next thing we need to do is really with this pi network, we're effectively imagining that we're going to split this L1, this inductor right here. We're imagining that we're going to split it in half and add something called a virtual resistor between there and ground. And the value of that virtual resistor is what I called Z center up there. So modifying that Z center value will kind of change the frequency response of the filter. So this is essentially an electrical filter that we've designed here. And what we want it to do is we want it to be selective at the frequencies of we're interested in, so the AM band generally. So that's why I put this at 1 megahertz, because it's kind of close to being in the middle. We could do 12 megahertz. That probably would be closer to the middle, but it's okay. So that is our QL for that. Next thing we need to do is we need to calculate values for the components that make up this pi network. Now, so we have a higher impedance on this side and a lower impedance on this side. And if we want to have equal power dissipated across this resistor and across this circuit here, then what we need to do is we need to aim for having a higher voltage and less current here, and then this will be lower impedance, so it'll be, more current and a little less voltage. So what we need to do is calculate the value of this C2 right here. Now I'll call this the reactance of XC2, just so we can keep track of it. And that is going to be equal to Zn, so our source impedance, divided by Q of the source. So that comes out to 25 ohms of reactance that we need this capacitor to produce. All right, and then we need, call this is our series reactance. Now you can design a pi filter with a capacitor here and 2 inductors instead. But I don't really have as much experience doing that, so I'm not going to. X series on the source side is going to be equal to Zn, so Z source, multiplied by QS. No, that's not right. That's not right. No, it's actually Z center. I forget that part all the time. So Z center times QS is the value. So this one half of the inductor, remember I said earlier we were imagining that we were going to split this in half. Now, this half of the inductor that's facing this side of the circuit needs to have 20 ohms of reactance, and this needs to have 25. So what we will do is we'll find the total reactance necessary for this L1 that accounts for both sides, and we will choose an inductor value that provides us that at 1 megahertz. All right, so X source load, or X series load equals C center times Q of the load. That needs to present 61.47 ohms. So in total, we need to present about 81.47 ohms of reactance on this L1. And we will label out all of our components later. X of C3 going to be equal to Z input over QL. All right, so that reactance needs to be 63.1 for this capacitor here. Now we can figure out our values by rearranging the impedance equation. So C3, or actually let's do C2 first, so it's all, needs to be 1 divided by 2 pi f, let's do X C2. All right, so that's our value for C2. C3 is going to be equal to 1 over 2 pi f times the reactance of C3. Beautiful. So 2.52. Let's go ahead and fill that in. 2.52202 nanofarad. And this one needs to be 6.36619 nanofarad. And our inductor, L series, is going to be equal 2 pi f divided by X SS plus X SL. That's not right. I think I have these backwards. So what I can do, instead of flipping the denominator and numerator around, let's just take the inverse of it and that will achieve the same thing. All right, so it looks like we need a 12.96 microhenry inductor. All right. That is our Pi network components. Now we can quickly check this to see how well the Pi network's doing. So what we want to do is check voltage just beyond this source. It should be very close to half of the 4 millivolts. Now watch this. If I make this a really large inductor, watch what happens to our voltage. It goes below 2 because this impedance is too great at this point. As frequency increases and inductance increases, the impedance as well increases. So we want to have this set to, a value that brings us pretty close to 2. That tells us that our match is pretty close. The other thing you can do to see how well Pi network is working. Sorry, I didn't put micro there. So now we're about 2.3, 2.2. Let's see what we actually are at. I hate if there's a way to just zoom in to something reasonable. You can see we're very close to 2 there. It's about 2.2. So that's a pretty good match that we've got on our Pi network. And the other thing I will tell you with a Pi network is if one is designed okay, generally the currents through all of these reactive components that make up the Pi network will be very close to equal. You see, when I'm clicking through them, the amplitudes are all really, really close. So that's another indication that we have a pretty good match. All right. So now we need to find our small signal base current and our small signal collector current. I'm also interested in V collector, the small signal collector voltage, and the small signal base voltage, base emitter voltage. All right, so VBE, honestly, we probably need to check it because this is a voltage divider equation. I'll tell you what, I may attempt this. I'll probably have to make a video on my phone with a pad of paper to keep track of everything because there's a lot of parallel branches and the math's going to get really confusing. So let's just for now, let's just go ahead and measure it. And if you guys would like, I'll make a video on how to analyze, you know, and do a voltage divider rule to figure out what voltage you'll have here. Um, so what we need to do is we need to take the peak amplitude, the peak voltage, and subtract the peak negative voltage. So a good way to do that is to place a cursor here, move it to the top. I'm going to copy and paste this, and then subtract the bottom voltage. That'll give us a base voltage to work with. All right, so okay. So you can see, look here. This is the beauty of the Pi network. So we had 4 millivolts here. We have 2.3 millivolts here. We have about 40 millivolts there. And then we've got, no, wait, no. We've got about 4 millivolts there and about 10 here. So you can tell we are trying to match this impedance by raising the voltage on the base, the AC voltage. And that way we get an even power dissipation through the transistor, through the base emitter junction. We get the maximum amount of power, therefore we get the maximum amount of amplitude. So we're not going to look at anything else yet. We're not going to cheat. We're going to try to solve it and then see if we are right or not. All right. So VC will always equal I sub C, so the small signal collector current, times the resistance of the output. Now, so what this is going to be the parallel combination. So it's going to be from here to ground through this shorted power supply. So we're talking about AC, so we need to short this. So now what do we see looking out from the circuit? We see this in parallel with this. So we need to come up with a value for R out. So R out is equal to 1,000, the inverse of 1,000, plus the inverse of 1 over 2 pi f c, or load capacitor, plus, so that's the impedance of that load capacitor. As you can see, it was really, really tiny, plus RL. All right, so we need to take the inverse of that, and then likewise, we need to take the inverse of the entire thing. That is not right. Oh, that's why. Take away this parentheses, make it cleaner. So it looks like we've got an output impedance of 545 ohms. We need to find IC. Now, IC in the small signal sense, and IB, no, let's start with IB. So IB is going to be VBE divided by R pi. And then if we would like, we can also account for this C4. Let's go ahead and do it. Just for the sake of accuracy. All right. So our base current should be 26.8 microvolts in amplitude. And then our collector current for AC, there's actually two expressions that can get you it. One is beta times IB. So beta times the small signal IB would give us our collector current. So that's 2.68 millivolts. So then that would give us a 1.46 volt swing on the collector. So let's just see how right we are about all this. 78 minus 51, that's 27 microamps. 26.8, that's really good. Really good. Now IC should be beta IB, so now we have 5.1 milliamps and 7.8, that's 2.7 milliamps. VC should be 1.46 volts. So let's do our cursor here. Let's go down here and do our subtraction. And now let's go down here to the bottom. Let's just copy and paste that one. 1.464, dude. Dead on the money, boys. Dead on the money. All right, so that's how you do a small signal analysis. Figure out these things. If you would like me to make a video on doing this analysis here to figure this out without having to physically measure it, just let me know. But thank you.